Okay, this is the torque, and when net torque is zero, it is equilibrium, and when torque is not zero, there is an angular acceleration. We are going to understand effect of torque, how to calculate torque, and its effect. And actually, when we talk about rotation motion in a way runs parallel to linear motion. All the terms you see, some when we take force is proportional to ma. A similar analogy is torque is equal to force is equal to ma, torque is equal to IL. And there we say an object is in case of translation equilibrium, net forces have to be zero. Here also, if object is not rotating about a particular axis, if object is in a state of rotational equilibrium, the torque has to be zero. And if the torque is not zero, then it will lead to alpha. That's what we need to do here today, angular acceleration. First, very quickly, let's go through what does torque mean. See, every angular term, what are the angular terms we come across? Angular velocity, angular acceleration, torque, angular impulse, and angular momentum. So whenever you use the term angular, that's a corresponding linear term, and whatever corresponding linear motion term we have, whenever you have angular quantity, it gets a cross multiplied by p multiplied by r term. R will always come first, and that quantity will come later. So even if I say, suppose example, if I take omega, now, omega also this also the direction omega is a cross product of r cross p. It's the equivalent of velocity. So velocity term gets multiplied by p cross multiplied by r term. But that, in terms of so this is the direction. But we know the magnitude has to be v by r, so that's the expression for omega. So every term which has angular, when we talk about angular momentum, again r will come. So which term? R will always come first for all angular terms. So r cross f with respect to point. So what is R here? Suppose this force is acting. This is the point of application of force. And unlike force is something which is independent of choice of axis. It doesn't depend. But torque depends on choice of point. Which point we are calculating torque about. So if we are calculating torque about point O, what we need to do here, what does R bar represent here? R bar represents position vector of point of application of force with reference to the point about which torque is being calculated. So it's always with respect to a point. And direction of torque, one is pretty simple. Since r cross f, you place r cross two vector tail to tail. So if this r vector, if you have to place tail to tail, keep this r vector here. And if I keep this r vector here, it's r cross f. You can curl my finger. If I curl my fingers in this direction, the thumb will find into the page of into the plane. And through that right hand thumb rule, we can find out direction of torque here. Or other way to understand also, whether this is the force acts here. And suppose this rod is always visualize r vector and clockwise and anti-clockwise. So just think of this as an arm of a watch or clock. This is the fixed point. If the force acts here, is this arm turning to be turning in the clockwise direction or anti-clockwise? If it is turning in the clockwise direction, it is negative. That's how fingers will curl into the plane of paper. If it is turning clockwise, it is into the plane of paper. And if it is turning anti-clockwise, if I turn my fingers in this direction, my thumb will point towards me. That's the direction. So any which way, either r cross f or clockwise or anti-clockwise, you can find direction of torque. Most cases, this clockwise and anti-clockwise is enough. R cross f is not necessary. So, typical majority of the questions, if we come across where r vector and f vector both are in the plane of the drawing, we know the cross product is always perpendicular to plane containing two vectors here. So if both are in xy plane, torque will have only k component. And how do you find direction of k component? I mentioned two methods. We can find direction of which direction it would be. It would be into the plane or out of the plane. In terms of magnitude, we could have written is equal to, so this is the angle between them, this is the angle theta here. What is magnitude is equal to r of sine theta. Or we can understand what is r sine theta. R sine theta is nothing but if I draw a line, that's the line of action of force. So if I drop a perpendicular and the perpendicular, if I drop this perpendicular, if I call r perpendicular, so and this is the lever arm. Another way to find the magnitude of torque is force multiplied by its perpendicular distance from the point about which torque has to be calculated. So this is a point and this is a line. What is the lever arm? Lever arm is perpendicular distance of a line from the point, and that should be simple enough to calculate. So when we, another important point is what you notice here, if I translate the force, whether this force is acting along the line. So if I shift not this point, I shift the force at another point which is on the same line, the torque does not change. So if I translate the force, anywhere apply the force, rather than applying here, I can as well apply it here. If I apply it here, it becomes easier to understand. R and F are mutually perpendicular. Let's take a very simple example. So there are two forces acting. Let's see how do we calculate torque here. Okay, so let's go to torque here. See, suppose this, let's first calculate torque about 30 Newton. What is torque of 30 Newton force? That statement is meaningless. First, I need to define about which point. So moment I say, what is the torque of this force about point O or an axis passing through O? In that case, since the axis lies on the line of action of force, it will have zero torque. So any force which is passing through an axis, its torque about that axis is zero. Perpendicular distance is zero. But same force, if I ask the next question, what is the torque of this 30 Newton force about point C here? Then it will have non-zero torque. And how would I find torque in that case? In that case, torque will be equal to, so I imagine this is a line of action of force. I multiply by this torque by perpendicular distance, which we call as lever arm. How much is the lever arm in that case? Lever arm in this case, we drop a perpendicular from here on the line. And when we drop a perpendicular, this distance being 2 centimeter, this is 45 degree. I can find the lever arm perpendicular distance is root 2. Similar way, torque of 10 Newton, that's one way I can take as perpendicular distance. What is the other way? Just look at 10 Newton force. So what is the torque due to 10 Newton force about point C? Now we can either use perpendicular, drop a perpendicular here, or I can use component. What does component mean? Let's understand here. I can resolve into two components. One is, of course, 10 cos 20. So 10 cos 20. And this force is horizontal, other force is vertical. So what you notice here, so what is the torque of this force? When the force is horizontal, perpendicular distance will be in the vertical direction. And vertical distance is zero here. And this case, force is vertical, so I'll measure the distance along horizontal direction, which is 2 centimeters. So vertical component here, and which direction it is trying to rotate. If this force or point C, if I imagine a line, if this force is like this, it is tending to rotate in this direction. It is like a clock is rotating in clockwise direction. Sorry, this arm is rotating in the clockwise direction. So in normal convention, the torque about C is along minus K direction. Clockwise is negative. Okay. Similar way, let's look at one more question here, just to quickly understand here. So this is the center here. 1, 2, 3, 4 forces are acting. And the point of application is given, and the directions are given. And we need to find their torques here for each of the forces. Let's look at one by one. So each force, we'll take each force, let's in our mind calculate what is the perpendicular distance, which is lever arm, and whether it is what is the direction in terms of clockwise and anti-clockwise. All about which point? All about this point here. Let's start with the first one, 8 Newton. What is the perpendicular distance? I'll drop the perpendicular from here. And if I drop the perpendicular, if radius is 20 centimeter, the perpendicular distance is 20 sine 30, r sine 30. And which direction is trying to rotate? This one, if I look at this, it is tending to rotate in this direction, clockwise. It's negative. For 4 Newton is at 90 degree with r. That distance itself is perpendicular distance r. And which direction is tending to rotate? This about this point here. If I think of a needle here, which way this needle is rotating? This needle is rotating anti-clockwise direction. It's positive. 9 Newton. 9 Newton also is perpendicular here. And perpendicular distance is r. And which direction it is tending to rotate about this point if this force is acting? It's tending to rotate the wheel in the clockwise sense. On the object it is connected to. Clockwise is negative. Final one is 6 Newton. That is perpendicular distance is zero. Line of action of force is passing through the point C. So it is like zero torque. Okay, let's look at this question, the recent mains question here. How do you solve? This is a three-dimensional case. A slab is subjected. So this kind of slab here is subjected to two forces, F1 and F2, and both are of the same magnitude. Force F2 is lying in XY plane. So this angle 30 degree, this load is lying in XY plane. And F1 is acting along Z axis at this point. So point of application, this is given, its direction is given, and direction of F2 also is given. We need to find moment of these forces about point O. So this is what we need to find. And all cases, whenever multiple forces are there, we can find one after other. So let's first look at torque due to F1. See, in this case, we first thing we notice here, can we find component or not? Since the answer is in IJK form, it's better to use cross product here. So all I need the R vector. R vector is what? R vector is position vector of the point where force is acting. With respect to where the torque has to be calculated. Torque is calculated about O. What is position vector? Position vector is given. It's acting at point 2I cap plus j cap. Had they mentioned midpoint of the slab, still we could have calculated here. So we simply write this expression. That's the torque due to F1. And cross product we can easily find. Similarly, when we come to F1 here, F1 becomes a little tricky. This is sort of the next one, F2. So either you need to visualize, either you have to take components here. Because there are two ways. Either I can write F2 also, I can write in a unit vector form, or I take components. If I take components, what are the two components here? Let's mark those two components here in the second case. The two components will become like this. One will become like this. That will be equal to F cos 30, which will act along y-axis, and this won't act. This will not create any torque. So the component acting along y-axis will not create any torque. And this force in xy other component will be like this. How much this component will be equal to F sine 30. And this torque, and you can, so basically what I can do here, so this component I can go and I can calculate torque due to this. And how much will be the torque here? I can write this F also, or otherwise if I could have written F also in unit vector form. This angle is given 30 degree. If I look from the top, this is how it will look like. I can write this vector also in component form. This angle is 30. It means both an XY component. I can translate this because maybe a little easier. This force is F. This angle is 30. So what is X component? X component is minus F cos 30, and Y component is minus F sin 30 j cap. So I can write, and what is the point of application? Point of application is 6 j cap. So either I can take component and then I can write F sin 30 into 6 k cap, because I understand here once this becomes in this xy plane, which direction will tend to rotate. You just look at this, it will tend to rotate. And if I look from the top, it will tend to rotate in this fashion, this component here. So any manner, there are number of ways you can find an answer. Either I can take as component, or I can write force also in terms of unit vectors. Both way you can solve. This is in talk, otherwise this is a straightforward topic. Coming to question which is a little tricky. So all of you might have seen a mop. Mop is, some mop can be circular in shape. Circular, this kind of thing is there, and you keep on the surface and you press it down and you tend to rotate the mop. When you tend to rotate, it scrubs against the surface. So this kind of cleaning mop, as it works in a machine kind of thing, cleaning machine process. It has circular mop of radius r. With vertically down, it applies a force F in the downward direction. Where from you're looking, this is the top view. You're looking on the top. It's a vertical view. And in this case, when you apply a force, and it is rotating constant angular speed, so it is rotating with angular velocity omega. Force F is distributed uniformly over the mop, and coefficient of friction between mop and floor is mu. What is the torque applied by the machine on the mop? Just imagine if there's a mop here, I think intuitively most of you should be able to feel, if you press the mop harder into the surface floor and then try to rotate, it will take more rotating effort. You understand what is the kind of force you need to apply to press it down, and what is the kind of force you need to apply. You need to try to turn your hand. You need to turn your arm also to rotate it. But this is being done by the machine. So let's find out how do you find torque. So torque is force into perpendicular distance. You notice if an object is rotating in this clockwise direction, any point I will take, if I take this particular point, which direction is this point moving? This point is everywhere, every single point is moving in that initial direction. If point is moving in the tangential direction, which direction will the friction force act? Friction force will act, kinetic friction will act in the opposite direction. So basically, all points friction force is acting, and everywhere friction force is acting opposite to direction velocity. So if this friction force is df, torque of this friction force will be equal to magnitude force multiplied by the distance. And different point distances vary. How do I calculate torque? First thing what I do, since the distance is varying, I choose a small element which is at the constant distance, so that lever arm or the distance from point about which axis about which torque has to be calculated becomes constant. So whole circular disk I divide conceptually into several concentric rings. And so this is what you see in the blue color is the ring. So before we do so, other things, since the force is uniform, so any small area I take, what is the force which will act? Force will be equal to, I can calculate what is the force per unit area. Force per unit area is total force divided by total area. That's the force acting. So when I take a ring, so I can calculate torque acting on each ring separately. Torque on several concentric rings. I have taken one random ring. Radius is r. Outer radius is r plus dr, or other way of saying thickness of the ring is dr. Dr tending to 0. So on this ring, it is every point on the ring. So if I take a small piece of the ring here, this ring has a velocity r omega in this direction. But friction force doesn't depend on the velocity. Since it is moving in this direction, friction force will act in the opposite direction. This is the direction friction force is acting. So if I call this force F on this small element, how much will be the friction force here? Friction force will be mu times the normal reaction acting on this small element. And everywhere, if I calculate here, everywhere the friction force will be tangential. Okay. So if I calculate torque due to small element, F into R, this also F into R, F into R. All small parts is F into R, all are in the same direction. So hence to calculate torque on the entire ring, how I calculate torque on the entire ring, see that one. So area of the ring, first let me calculate. So what is the area of the ring? Why I'm calculating area? Then only I can calculate what is the total downward force being applied on the ring, and that downward force will be equal to normal reaction. First, I have to calculate normal reaction. Based on normal reaction, you can calculate what is the friction force will be mu times normal reaction. And then after we have friction force, I can calculate what is the torque on the ring. That's a sequence. So area of the ring, we can calculate normal reaction, area into force per unit area. Then what is the friction force acting? Magnitude of friction force is equal to mu times dn. And what is the torque here? If I see, though the friction force is acting at different points, torque created by all friction force are in the same direction. So I can add up all the torque. So basically, I could have written what is the torque due to small element. Torque due to the small element would be, so what is the friction force acting on that small element? I could have written a df into r here. But when I add up for the entire ring, I am adding up all the friction forces, r being constant. So when we calculate torque here, torque is equal to total friction force on the ring multiplied by r. What is friction? Friction force. First, I'll calculate friction force. Friction force will be equal to mu times normal reaction. That becomes total friction force. All are acting tangentially at the same distance. Hence, torque on the ring is equal to total friction force magnitude. We serves adding up all the magnitude into R. So this I calculated normal reaction, friction force multiplied by R. That's a torque on the ring. But I have to calculate torque on the entire disk. If you calculate torque on the entire disk, we'll all are acting in the same direction. Though it is vector quantity, since all are in the same direction, we can add it up through integration. That's the resulting torque. So this is one of the more difficult, little more difficult question. This is something I think this level of question all of you should prepare for. Okay, coming to application of torque in terms of rotational equilibrium. The moment we think of word equilibrium, we have dealt with translation equilibrium, x0, y0. We get two equations, translation equilibrium in in two dimensions. When we have rotational equilibrium, it means alpha also is 0, it means torque also is 0, additional condition. So when we calculate torque, if it is rotational equilibrium, it means it's not rotating with respect to any axis. So I take torque about any axis, it comes to 0. Talk about any axis I can choose. I have choice, I can choose any axis. That's a facility we have. Let's take a simple example, and this is very common and example to understand rotational equilibrium. So there's a plank here, uniform plank of length L, and it is supported at 2 points. So you can just imagine if there's a plank, you can support at any different point, and depending on which 2 points you provide the support, the reaction force will vary. The reaction force will adjust itself to maintain rotational equilibrium, and if the plank is uniform and these two supports are kept symmetrically, they will have support equal weight. So they will have normal reaction equal to half the weight. But if they're not symmetrical, it will not be equal to half the weight of the plank. And this is something comes from rotational equilibrium. So not only there is a plank of mass m here, another what you call as mass of small dimension, you may treat as a point-like mass. Mass m is placed at distance L by 3. Moved at distance L by 3, its dimension of this mass is small and plank dimension is large. Find the reaction at support B. If that is what we need to find here, this is a typical example. So first thing what we do, unlike linear motion, I cannot represent the whole plank with a point because it involves torque as well. I just mark all the forces which are acting, normal reaction, mg acting at the center mass, this capital Mg acting at the center mass of the plank, which is at the midpoint. It is acting distance L by 2. So these are the forces acting. Now I can take summation of force in y direction 0, summation of force in x direction 0, and you can take torque also 0. What I'm interested in finding, what we need to find here, these are two reactions, Ra and Rb. So we need to find Rb, and it has to come in this form. So since I need to find Rb, it's best to have equation which does not have Ra. Ra is an unknown. How do I eliminate R1? I'll take torque about A is equal to 0. If I take torque about A is equal to 0, Ra will not go into picture because this torque about A itself is 0. So if I write this equation, this is turning anti-clockwise. This is one sense. These two are in the opposite sense. This is a positive torque. About this point, if other forces are not there, it would have rotated the plank in anti-clockwise direction. Or I can use R cross F. What is R direction at B? R. Since I'm calculating torque about A, I will take R with respect to A. So this is R and this is F, R cross F. If I turn my fingers, it will point towards me, which is positive. So RB multiplied by the distance. So that's all is fairly simple. This is 3L by 4 minus mg into L by 3, capital Mg into L by 2. We get this equation. So this is kind of equation, and whenever such cases are there, we can apply. And so what we notice here, again, I stress on one point here. Choice of axis makes question little simpler. You can choose any axis. You can take torque. If I calculate torque about this point also will come to 0. This also will come to 0. At any point I choose, you'll find the torque will come to 0. Next question is kind of ladder kind of question. Ladder also is a rotational equilibrium question. Every time when we have rotational equilibrium, we have additional condition that any axis I choose, if I take torque about all forces acting on the object, about that axis will come to 0. So ladder is leaning against a smooth wall. A smooth wall means whatever force acts, it is normal to the surface. There's no tangential component, no friction. And rough surface. The surface is rough, this is smooth here. Find the friction force acting here. If I have to find this uniform rod, mass is m, length is L, and it is leaning at angle theta from the horizon. Again, this is a question of rotational equilibrium. It is an extended object. So let me mark all the forces. So what it done similar here. Here I have marked only the normal reaction here, RB. Mg is acting at the midpoint. And at A, since friction is also present here, the contact forces, normal reaction as well as friction. And what we need to find, we need to have friction force acting. And we have three equations here. What are three equations I could have made use of? I could have written as summation of force in y direction is 0, 0. If I write summation for y direction 0, very easily I get this normal reaction will be equal to m. Entire weight, whatever weight is there, entire weight is supported here. And second thing we get here, in terms of magnitude, F is equal to RB. These friction force and normal reaction, they are in the opposite direction. But if I write as Fx is equal to 0, still I don't get the value of F. How do I get F? How do you get friction force? I can take torque, if I take torque about A is equal to 0. If I take torque about A is equal to 0, these two will have 0 torque because both are passing through the point here. So moment I choose this axis, this torque about A is equal to 0, it has non-zero torque only by two forces. It's always better to choose axis about which most number of forces are passing through. So if I talk about zero, this force is vertical. So perpendicular distance will be the horizontal part. What is the horizontal part here? This is L by 2, this angle is theta, L by 2 cos theta. And this force is horizontal. So perpendicular distance will be in the vertical direction, which is equal to L sine theta. We write those torque, and this is tending to rotate about this point. This is tending to rotate in the clockwise sense. This is negative, and this is tending to rotate in anti-clockwise sense, and this is positive. Or I could have done an R vector here. If I take what is the R vector at this point, R vector is like this. This is R cross F. This would have been R vector at B. R cross F, if I do fingers curl like this, it will point towards me. And what you notice if this angle here, what happens if a theta changes? So let's try to understand what will happen to normal reaction here at B. The normal reaction as theta becomes smaller. Smaller means if I make this ladder shift like this. If I make a shift like this end will move, another end also will move. It may become like this. Angle has become smaller. What it says, what happens when the angle becomes smaller, theta also becomes smaller, and this value will become greater. So what will happen as the theta keeps getting smaller, friction force becomes required to keep it stable, keeps increasing. And at some point of time, as we keep making angle smaller and smaller, it may not remain in equilibrium. So what is the minimum angle at which it will remain in equilibrium? Moment we talk about minimum angle is friction force will be limiting friction. So when an angle becomes theta is minimum, in that case, friction force will be equal to mu times normal reaction, which is mu times mg. So for angle theta, when this value becomes equal to mu mg, that would be the critical angle up to which it can remain in equilibrium. And in this you can notice, if you keep this at a larger angle, ladder is more stable, and as the angle becomes smaller, at small angles, it will not remain stable. And this also another kind of question, and it can come in different forms. Just understand this. I think you'll find no difficulty at all. You might have seen that some of the ladders we have at home and other places also may have something like this inverted V shape and is connected with the hinges and is something like this. It is made of so it could be plank, it could be rod, but if I look from this angle, even if it is a plank also, it looks like a rod. So inverted V made of two uniform boards, smoothly joined and each weighing 200 Newton. So this also each weighing means what? Left part also 200 Newton. So its weight will act as center mass, and because of uniformity at the midpoint, this is 200 Newton, and other side also midpoint is 200 Newton. So if I look at the whole thing here, of course the normal reaction here also has to be equal to 200 Newton because symmetry, and they will have equal because these angles are equal here. Question what is asked here, what is the similar to previous question, what is the friction which will act at this point? Here also friction will act, and even here also because symmetry, both forces are like mirror image, friction will act. Yes.
So there won't be any like vertical force acting at that hinge on top there. Like how can you say
No,
that
it
the
will not
force?
have any vertical component. And it's very easy to understand why it will not have vertical component, because both are like mirror image. If I take left part separate and right part separate, both have to have at least mirror like forces. If one of the object force acts like this, other object also force becomes like this, and then becomes net force in the downward direction, which is not possible. So forces have to be because of symmetry, and that's why I was coming to. So what is the friction force which will act? How do I find it out? One way of thinking this question, just think of it. If I just cover the right part, if I just look at the left part is identical to previous question, ladder leaning against a wall. How do I find friction? I take this as a left part as a free body diagram, and this is the contact force. The right part is applied at the hinge, and this forces you can vary. I think a little bit. This reaction which is being exerted here, and very similar way I can find friction force. If I talk about the zero, I can find the friction. Just imagine here, if it is kept on a roller, if it is kept on a roller, and suppose there's no friction here. If we kept on the roller, what will happen? Moment we keep it, both the legs will start spreading out, and this will have a downward motion. It will fall flat on the surface. So other way friction is not there. How do I keep it stable? I can connect these 2 points. I can connect by a rod or a wire between 2 points. So if the question is, if the ground is smooth, but lower ends are connected by string, what is the tension in the string? So if there's no friction here, if I connect by string, actually string also will apply the same force what friction would have applied. Friction applies force at this point here to make it stable. The string also applies at the similar point, very close to this one, but the string applies a friction like this kind of force, contact force. Because of stability, nothing else has changed. So whatever friction force would have acted for a particular angle, now tension will act at a similar angle. So friction is not there. If I put a T here, it's nothing. T is replaced with F is replaced by T. If again I do, I can find similar answer. And it becomes a little more challenging if I say no, the ring is not string is not tied here. The string is tied at this point here. If the string is tied at this point here, what would my free body diagram look like in that case? In that case, also I can easily solve. Let's see if the string tied at some other point here. In that case, if again I take only the left part, again I convert into whenever the symmetry is there, I take only one half. It becomes like a ladder kind of question. Suppose the string is tied at some point which is L by 4 from here, bottom. And this angle is theta. If the string is tight, if I take this as a free body diagram, if I take the left as a system, there is a reaction force acting here. And there's a normal reaction here. A normal reaction very easily can come, it will equal to 200 Newton. And if the string make it stable, this tension force is acting. How do I find tension force again? In this case, to find this tension force, if I talk about this point B is equal to 0. If I take talk about B is equal to 0, it will be n into this time distance and T into T is horizontal, T into vertical distance. These two have to be equal and opposite. I can find T here. What I notice here, if the string is fixed at the larger distance, tension required will be smaller. You can check that point out. So T will keep reducing as it is closer to the bottom surface. Okay, some more question on equilibrium. So far, I'm still dealing with the questions on equilibrium. Uniform cylinder of mass m is wrapped as a light string. So you can do that also. If you have a rough surface, take a cylinder, run kind of string around it, and string it tight like this, and you arrange the cylinder in such a way that the string is parallel to the inclined plane. And you notice here, this will remain in equilibrium if you remove your hand or if you remove the support from the cylinder. If it doesn't slide down, it has to happen only because there's a friction here. Without friction, it would not have remained at rest. So what is the tension string and friction force here? Again, this question is of equilibrium. So let's first identify what forces are acting, and I can apply additional condition that talk about any point is 0. So again, since the string also acting along the inclined plane, let me take this direction only as x-axis and perpendicular to this as y-axis. So if I take that one, because normal reaction, friction force, everything x and y axis is much easier. So the weight also I need to express in this form of component form. If I take x and y axis, this part becomes equal to mg sine theta. So this part is mg sine theta, and other component is equal to mg cos theta. These are forces acting here at center mass. These are the forces acting at center mass. What other forces acting? Normal reaction. Contact forces here. The contact force here will be equal to N. And the friction force act, we don't know which direction will act. We can mark any direction. And then we see later if the marking is correct or not. And if I'm looking at this is also contact string, there's a tension acting. 1, 2, 3, 4, 5. These are forces acting. And if I write summation of force in y direction 0, it easily gives me that normal reaction is equal to mg cos theta. Here also normal reaction will not change. Normal reaction will remain mg cos theta. Now, if I take summation of force in x direction 0, I find friction plus tension is equal to mg sine theta. So mg sine theta will be equal to frictional force plus tension force. So this is equal to friction force plus tension. But if I want to find tension, I can take a torque about the bottom contact point to be 0. So this is a point of contact at the bottom. If I take a summation of torque about point P is equal to 0. And like usual, I take anti-clockwise positive. About this point, normal reaction and friction force both will have zero torque. Both are acting at the same point, at the point of contact. Only two forces will have non-zero torque, mg sine theta and t. Mg sine theta is acting at perpendicular distance r, and t is acting perpendicular distance of 2r. T is having positive torque about this point, anti-clockwise. Mg sine theta is clockwise. Let me write t into 2r positive and minus mg sine theta into r. So that gives me value of t is equal to mg sine theta by 2. And once I have t value, the friction also is equal to mg sine theta by 2. So question may also come, what has to be minimum value of frictional coefficient of friction for it to remain stable? Moment I write minimum friction for minimum condition, basically it is a limiting state. Friction has to be equal to F max, or in that case, F has to be equal to mu times N. I can find value of mu. This is equal to mg sine theta. You can find this. Okay, this is a little different question. This is something what you see every day. And if you, in your room also, if you look around, you'll find the door frame. Typically, I think you'll find three hinges are connected. Olden days, you'll find some of the doors will also have two hinges connected. And door also, this is something, if I take a vertical axis passing through the hinge, the way the hinge is designed, it can rotate about a vertical axis. And we are looking the side view of the door of Almira. It could be your door also, Almira shutter also, like 6 feet high, and dimensions are given. Okay, and weight is given. If weight is given, which point the weight will act? Weight will act as the central mass. Let's say this is equal to 80 Newton. This weight is acting. Okay, and door is supported on two hinges situated at a distance of 1 feet from the end. There is a distance also is given. So this is 1 feet from either end. So the matter we shall try to understand how to solve this question. This is a little different from majority of the questions of rotational equilibrium. What is given if magnitude of force is exerted? See, if I look at this question here, whenever hinge is there, hinge can offer forces in both directions. It's not like a smooth surface. Hinge can have a horizontal component as well as vertical component. It may have a horizontal component as well as vertical component. And if there are two hinges, there are two forces on the upper hinge, two forces on the lower hinge. You will have four unknowns, whereas we have only three equations. And what are three equations we have? Fy is equal to 0, fx is equal to 0, and torque. So that's why I need additional information to solve that question. And additional information is given. Magnitude of force exerted by the hinge on the door are equal. So in this case, if forces are equal, so first of all, if I call this as V vertical component, and this also vertical component, both have to be equal magnitudes. So this vertical component will be equal to 40 Newton. So vertical weight is evenly supported by vertical reaction on the hinge. Now, when we come to horizontal part here, horizontal part magnitude have to be equal, but is it possible that both can act in the same direction? Impossible. If both act in the same direction, the net force becomes in the horizontal direction. So for magnitude to be equal, both have to act in the opposite direction. And there are other reasons also, because of rotation, they have to act in the opposite direction. If I call this point as A and this point as B, if I take torque about A is equal to 0, you notice how many forces are acting? 5 forces. But out of 5 forces, 3 forces are passing through point A. This force, and even this vertical reaction here. So only 2 forces are non-zero. Force non-zero is mg and reaction B, horizontal component. If I take torque is equal to 0, I get this component. And which direction this component has to act? This is creating a torque in the clockwise sense. This has to create torque in the anti-clockwise sense. So top hinge, the force has to act which direction? Basically, when you try and imagine, suppose rather than hinge here, you put in a string. If you hold the door frame, what do you know? You have to pull, you have to apply a force, of pulling force to hold this door frame in a state of equilibrium. So this is the direction which the force will act on the upper hinge, horizontal component, and bottom part, it will act in the opposite direction, right? These two forces create a couple. And if you look at this, these two vertical components also like one force, and these two create a couple. They create equal and opposite couple. So vertical component and weight creates a couple, which is having this kind of sense. And these two horizontal components create a couple which is in the opposite direction. And that keeps it equilibrium. So there's some more questions on equilibrium. And you notice, Mother, see, if you suspend any object from a particular point, it comes to rest only a particular orientation and any shape you take. So here what you have taken, suppose you form two rods, you take two rods, but two rods not of the same material. They're different material, that's why masses are unequal. So you take two rods of equal length but different masses, they're joined in form an L-shaped body in 90 degree. And at the point of junction, you make a small hole, smooth hole. Either you put a hinge or you suspend with the thread. When you suspend with the thread, it will always form a particular angle. It doesn't matter who hangs it. I hang it or any other student try to do something. You'll always find it will come to equilibrium at a particular angle. So in this case, the angle given is 30 degree. This angle will depend on the relative weights. Let's try and understand this kind of question, and this kind of question can come in different forms. But all forms have a common principle to solve here. So basically, I can, if I look at this particular object as a system, M plus capital M is a system, what are the forces acting on this system? This system, wherever it is suspended, if it's suspended by thread, a tension force is acting. What other force is acting here? Other forces is weight is acting. And if I take the whole thing as a system, I can show the entire weight acting as the combined center of mass. So if I display the combined center of mass, see, if it is in equilibrium, two forces have to be equal and opposite. Tension has to be equal to the weight. And second part, the torque also has to be zero. And torque will be zero when they are in the same vertical line. Otherwise, two of them, if two forces are not in the same line, it will create a net torque which will tend to rotate. So what is the important point when we have to understand here? Whenever we suspend any object, the center of mass, combined center mass of the object must lie vertically below point of suspension. That's a condition for rotational equilibrium. So what is given here? So this information indirectly tells if I mark the center of mass, which is a point. If I connect center of mass with this point here, the line joining center of mass with O makes an angle of 30 degree with the mass which is having capital M mass. Now this orientation, see this center of mass doesn't depend on orientation. What I do, I take this L shape out and again I rearrange it. I kept it like this. I have removed this one from here. I kept it like this. When I keep it like this is center of mass. What is the information given here? Information, if I connect, this was the point of suspension here. As per the information given in the question, if I connect this line to center of mass here, this C point was here. This COM makes an angle 30 degree. COM, this angle is 30 degree. That's a question. Now it becomes a simple question of finding center mass. The center mass will have axiom in this orientation. Basically, I have changed the orientation so that it becomes easy for me to understand. I can calculate axiom and YCM, but since angle is 30 degree, angle 30 degree means what? If this angle is 30 degree, axiom by YCM is equal to 1030. That's what condition given. So 1030 is equal to axiom by YCM. What is axiom equal to? This entire mass M I place here and M into L by 2 and this capital M to L by 2. What is axiom equal to? Axiom is equal to M into L by 2 divided by M plus capital M. Similarly, I can find YCM and substitute the ratio. I can find capital M by small m ratio. And this question, any shape. So in case of this, suppose I suspend, you can try that one. If you take a semicircular ring, if you take a semicircular ring, and it remain like this note, when you suspend, it may take some shape like this. So the basically semicircular ring will get suspended like this. And you can try that. So take a semicircular ring, uniform ring, and when you suspend here, you find this also, the line joining two ends of the semicircular ring will not be vertical. And why it takes suspend like this? Because when I look at this, the center mass here, the center mass has to be vertically below. And we know what is the center mass of circular ring, semicircular ring, it is equal to 2r by pi. It will get suspended so that this will be 2r by pi, this will be r. That's how angle it will form. Any shape we take, the center mass will always be vertically below point of suspension, so that the torque becomes zero. Forces acting, weight and tension. Okay, perhaps I think last question on rotational equilibrium. This question is, see, you can imagine, yes, you can do that also. If you have a smooth surface and you keep a cylinder or sphere, it doesn't matter. All cases you get a similar answer. It could be cylinder, it could be hollow sphere, it could be a disc, anything. It is answer is similar. What is the minimum height of the obstacle so that the stair can stay in equilibrium? So we are keeping an obstacle here. If we leave it like this, of course, it will start rolling. If I keep a small piece of wood block here, wooden block, it will just ride over the block. I have to have minimum height of the block to keep this sphere at rest on an inclined plane. Okay, let's understand. So condition for being, so one way we have to find minimum height. Minimum height is whether it has to be on the verge of equilibrium. It means if it is slightly smaller, it will roll over. If slightly larger, it will keep in a stable state. So when a minimum state means is on the verge of rolling over. And you can imagine if I keep a very small object here, what will happen? It will, you can just imagine to roll over. And what does rolling over mean? When it rolls over, just before it rolls over, the normal reaction tends to become zero. That's what will happen, rolling over. Rolling over means this normal contact between sphere and the surface will get lost. So as we keep increasing, the normal reaction will keep changing. So normal reaction has to become zero for it to roll over. That's one point. Then we look at if the normal reaction becomes zero. Then again come back to same situation. Then if normal reaction is becoming zero on the verge of rolling over, we are examining the condition is on the verge of rolling over, normal reaction has become zero. If normal reaction has become zero, then there are only two forces acting. What are the two forces acting if I keep a block here? If I keep a block, only two forces will act. If I keep a block, which are the two forces acting? Two forces acting is the contact force at this point and the weight. The moment there are two forces, it is on the verge of equilibrium. These two have to be in the same vertical line. So what should be the minimum height? Minimum height of block, if I keep the block of this height here, this contact point is here, it will exert a force in the radial direction if the surface is smooth. This will exert a force, but it will have a net torque, it will ride over. The condition is the point of contact has to be vertically below. And what if point of contact is vertically below, it becomes very easy question to solve. If this angle is theta, then from here, if I complete this triangle, okay, I complete the triangle like this, and this is height h here. If this height h, this angle also is theta, radius is r, and this is height h. What is this height h equal to? Height h is equal to r minus r cos theta. Height h has to be r1 minus cos theta. If height is equal to this, is on verge of sliding over, normal reaction is close to zero. If it is more than that, it is in the state of easy equilibrium. So if I keep a block like this, if the block is smooth, it will exert a reaction which will pass through the then three forces will act. And when we keep a block like this, normal reaction will not be equal to mg cos theta, which can easily be calculated. Right. Well, okay, sorry. One more question. This also several question I have taken are from some question. This also passed my mains question. Several of the question I have taken are some related to mains question. So if you have a uniform rod AB, just imagine that you have a rod AB. It's a heavy rod, and you have a strong thread or steel wire, and you can suspend the rod. You can tie the round around the rod and suspend at different points. And what are you doing here? If you suspend at the midpoint, of course the rod will remain in equilibrium. But if you suspend nearer to the left hand, what will happen? This will tend to go down. And just imagine if you want to prevent it going down, where if you have to apply force with your finger, if you have to press down at end A, if you press it down at end A, you can hold it in the state of horizontal equilibrium. You notice if this x is small, if this distance is very small, this distance is large, you have to press with a larger force. If x keeps increasing, the force what you need to apply in downward direction will keep reducing as x increases, and the force required becomes zero when x is equal to L by 2. So the force what I need to apply here in vertical downward direction to keep the rod horizontal is a function of x. What they're saying, what has to be if this is the value of x, rather than applying a force, here force is applied in terms of counter weight. So what is the value of mass? I need to suspend at end A depending on x here. We can these two quantities are related. So m and x are related. Question is, so they have a set of m and x. 1 centimeter I have some x. So we have a set of mx. These two quantities are related. So we record these two quantities. So which two quantity I should plot so that the plot is a straight line? Should I plot m against x, then I'll get a straight line, m against 1 by x, m against 1 by x square, or m against x square? If I plot, so basically one of the quantity I'm taking as on the x coordinate, and this quantity I'm choosing as y. If they form a straight line, one of the quantity here. So which of the other quantity I have to take so that when I plot, these two quantities have a kind of linear relationship. The graph should come as a straight line. Y graph should come from y is equal to mx. So first what you need to do, I need to find equation between m and x. Then I'll see how the linear relationship is formed. And finding relationships is starting from something what I explained now. If gas increase to L2, lower mass will require. Okay. So need equation between m and x, and very easy to find equation m and x using rotational equilibrium. If I take talk about x is equal to 0, two forces only are acting. Which are two forces? One force, of course, is mg acting at ma. The other force acting is weight, which will act as center mass. So this other force will act always at the constant point at a distance of by 2 from here. These are two forces acting. If I talk about x is equal to 0, naturally you can see one of acting is in the anti-clockwise and other is clockwise. So this is positive, other one is negative. So what we equate, so we take it to other side. Mg into x is the torque due to this one, and this will be mg into this distance is how much? L by 2 minus x. So this is x and this distance is L by 2. So L by 2 x minus x is other distance here. So I get a relationship between, I need equation between m and x. When I write an equation, it comes something like this. So if I plot between m and x, will the equation be linear? No. If this is my x quantity, if the equation between x has to be linear, this quantity here has to be equal to, should be plotted on x-axis. Which quantity will make a linear equation? 1 by x. So I need to plot m against 1 by x. If I take m is equal to x quantity, and if I take, sorry, if I take m is equal to y, and 1 by x if I take is equal to x here, what is the equation become? Equals y is equal to mg by 2 in place 1 by x minus m. That will be the plot. 1 by x, what has to be plotted? 1 by x. Had I this denominator, had I come as x square, I should have plotted m against 1 by x square. Had x come in the numerator x square, I need to plot m against x square. So it depends on how the equation form. So depending appropriate value of quantities need to be chosen, then only we get a linear plot. Okay, next question. Okay. A cubical block of mass m and HL. So this is a cubical block. We see only one face of the cubical block. It's sliding down on the inclined plane, angle theta, with a constant velocity. It means it in a state of, it's in the net forces on acting on is a zero, and its orientation is not changing. It means there's no rotational tendency, no rotational acceleration. Torque also has to be zero. So what we need to do, okay, this one something, if we net forces as sigma f x 0, sigma f y 0, torque also about any point has to be 0. What we need to find here, what is the torque exerted by the normal force acting in the block about its center? So I need to find, not net torque is 0. It is not, question is not asking the net torque. If this is the center, various forces are acting in, if I want to find torque due to normal reaction. And normal reaction, if you calculate in the normal way, you get a wrong answer. How do you get a wrong answer? Typically, what we do, we say, okay, normal reaction will act at the midpoint and it will pass through the center. Its torque will be 0. No, that's not correct. Why that is not correct? Let's try and understand. And to make you understand, I'll give another example, and which I think I've given last year as well. So suppose we have a block here. You keep a same cubical block. If you keep on a horizontal surface, you keep on a rough horizontal surface, something like a carpet. If you keep on a carpet, coefficient of friction between carpet and block is high. And when we normally keep the block, if the block is cubical block is made of uniform material, it will, wherever it is resting on the horizontal surface, if the surface uniform, it will exert constant pressure everywhere. The pressure exerted on the contact surface will be uniform. So it is kept like this. Pressure is uniform on all points on the base. All small areas pressure is uniform. But moment I apply force like this here, if I apply force, some horizontal force here, the pressure will not be uniform. If I look from the side, which side the pressure will be more. Moment I apply force and force is large enough, this end has to get lifted up. Why it gets lifted up here? The normal reaction in this end has become zero and this end become more. If I look at the normal reaction becomes only like this. So when you apply a force, why this becomes like this? Here also what has to happen, if I look from the center of mass, moment I apply force like this, it is creating a clockwise torque. So here also the normal reaction acting on the surface also has to create an anti-clockwise torque. So what has to happen, if I look at this, if this is a normal reaction, total has to be equal to mg. But when you look at this here, the left hand side force has become smaller, right hand side force has become larger. Any object, if I take, if I see, suppose here, if this are also force acting F and this also force acting F, the torque becomes zero. It is not creating a net torque. But if this force is F by 2 and this force is 3F by 2, it is creating, so basically F by 2, F by 2 are calculating equal torque. This is creating a net torque. So as to create a net torque, to keep it in equilibrium, this side pressure becomes more. Hence, effectively, the effective point where normal force is active is not at the center. Effective point is shifting. When no force is applied, this way normal force is acting. As we keep increasing F, the normal reaction also will keep shifting away. It cannot go beyond this point. When it comes here, then it rest of the surface loses contact. Only one point, the edge of the block only remains in contact. So here also when it is sliding, here the reaction is not uniform. The lower part will experience larger reaction, upper part will experience lower reaction. This also mg is trying to tilt it. And because of it, we can assume the normal reaction not acting the midpoint, normal reaction is acting at a certain distance. What is the distance? We don't know. We don't know what is the normal reaction here, but we can find torque in some other manner. How do you find torque? We find something else which is equal to torque created by normal reaction and something else which can be found. That's the image. We cannot find normal reaction here because we don't know how the distribution is. We can't find. Let's understand, if I calculate torque about the center, there are three forces acting on this. What are three forces acting on the block? Net force has to be zero. One force acting is its weight here. Second force is acting is frictional force. And third force acting is the normal reaction. When I take torque about center is equal to zero, out of three forces, one torque is zero. It means other two torque due to friction and torque due to normal reaction are equal and opposite. When they are equal and opposite, so in rotational equilibrium, let's talk about any point in the Q must be zero. So if we take a component mg, normal reaction is zero. So what you need to do we know the frictional force here? Can we calculate torque due to frictional force? Yes, we can calculate torque due to friction force. So friction force also, wherever it is acting along the surface. Friction force also, there's more friction force acting in the lower half, lesser friction force acting in the top half. But all friction forces, the distance from the center is constant. And what is the total magnitude of friction force? It is equal to mu times total magnitude of normal reaction. The magnitude of normal reaction not changed, only its distribution has changed. So what is the total friction force? Mu times mg cos theta. And so what is the torque of frictional force? How we calculate torque due to friction force? Okay. What I've written here? Mg cos theta. Sorry. How I written it? Torque due to friction is mg cos theta. And the perpendicular distance is e by 2. Everywhere, perpendicular distance a by 2. That's torque due to friction. And torque due to friction is anti-clockwise. Normal reaction will be the clockwise, but that's the magnitude. That's how we calculate torque due to normal reaction. Yes.
So why can't we take the frictional force as mg sine theta, sir? Because it's moving with constant
Sorry,
velocity, right?
my bad. But what I wrote is correctly only. Sometimes I not that way. So it's correct only written. See, before I do why I'm writing this one, what is the friction force acting here? Friction force, if we take summation of force in x direction 0, friction force it is static state. It is not into kinetic state. Friction force is equal to mg sine theta only. It cannot be mu mg cos theta. Friction force is equal to mg sine theta. Okay. Why it is mg sine theta? Why it is not mu mg cos theta? Why I'm writing mu mg here? Both have to be equal. It's not in the kinetic state. Mu is not known here. Mu value is not known. Both are equal. It will also equal to mu mg cos theta, but mu value is not known. Thus, I have to write in terms of mg sin theta. Are you clear about this part?
Yes, it's in kinetic state only, right? So here also.
So it is in the kinetic state.
Yes.
It will be mu mg cos theta, but mu is not given. We need to write in which form? Yes, both forces. What are the forces acting here? This is mg sin theta and a normal reaction and friction force. If I take this as x direction, mg sin theta has to be equal to mu mg cos theta.
Yes, sir. So the magnitude will be same, right? So for the normal
The
reaction
same,
only
but
for
I think mu
effective
term is
position.
not known, so we should better write in terms of mg sin theta. Otherwise, even mu mg cos theta is okay. Okay. So pressure on the lower part will be greater. That's why it is creating a torque. And this is an important point to be understood. Right. So I'll stop here. I think already a couple of minutes or more. And I'll continue from here in the next session. Okay.